Today I'm going to talk about three things mainly. So the first one is base loci, the bundle. The second one is Iitaka foundation, which I will call Iitaka fibrations as for the line bundle case, even though we will see in the vector bundle case they're not fibrations anymore. And the third one is semi-ample for vector bundle. So just some motivation. This has it's been a long, long. In the last years, I've been thinking about this kind of things for various reasons. But the original one was that I was working with Stefano Urbinati, and I was asking him, what is the right generalization of, let's say, numerical equivalence, but for vector bundles? And then eventually we did not find out the right generalization for numerical equivalence, or at least some convincing generalization. And we started looking at numerical properties instead. And as for line bundles, numerical properties are connected to base loci. So we wanted to define those base loci. And by loci, I mean that there are several kinds of base loci that we can consider for a vector bundle. Then I will try to sketch those. And therefore, we were trying to give the right definition for vector bundles and then see what kind of numerical properties, or rather the numerical positivity properties of vector bundles that this base loci could determine. Positivity. So let me begin with the setting. Let me fix setting for what I want to talk about. By X, I will mean generally a smooth projective variety over C, but in some cases also a compact complex. Okay. And then, in the two cases, a vector bundle will be either an algebraic vector bundle over X or a holomorphic vector bundle in the compact complex case. So if we do fix a vector bundle, we have the projectivization construction that Chris talked to us about. Let us fix a vector bundle. Then we have the projectivization of E over X, and we can use the definition that we given the day before yesterday, which means that the proj scheme over X of the symmetric algebra. The important fact is that this is the projectivization of E, meaning the rank one quotients of E. So in particular, the fiber over a point X is the projective space over the fiber of E, and this is the space as rank one quotients of EX modulo isomorphism. Together with this projectivization, we do have a short exact sequence of vector bundles. Which restricts to each fiber as the Euler sequence. And we will consider so O1 as the universal rank one quotient of the pullback of the vector bundle E to X. Okay, then there are general notions for most of, let us say, algebraic positivity properties of E. And by algebraic, I mean those positivity properties which, despite the name positivity, they do not depend on the metric, of the choice of a particular suitable metric on it. And this is usually the reference is Lazar's book. And the idea is that the positivity of E positivity properties of E are related to positivity properties of this line bundle over P. By definition, of the line bundle over so E as a line bundle over X as a vector bundle over X, and this is a line bundle over P. And for example, we say that E is ample if and only if O1 is an ample vector bundle over P, and similarly for NEF, big, and so on. So for line bundles, what happens is that those positivity properties of line bundles, these are related with the so-called asymptotic base loci. Even for a line bundle. Then in the first work concerning this kind of topics, together with Alex Coronia and many other authors, where 6, where N is me, we define the right, or at least in our head, the right generalization of this base law for vector bundles. And this base loci that we constructed were the one which is called the stable base locus, then augmented base locus, and then the restricted base locus for E. So what we wanted to relate was some locus inside X and some positivity of the vector bundle E. Of course, one could look at the base loci for the corresponding line bundle PE, but this would be somehow a locus inside here. While we wanted to relate positivity with some properties of locus directly inside X. So we defined those and we related those base loci with some of the already existing positivity properties appearing in the image. For example, ampleness and netness are related respectively with augmented and restricted base loci of E. Today, I want to talk about the stable base locus, and I will define what it is and some of it. So, and somehow this seems more natural to be constructed and to be described, starting from the base locus of E and then passing to what is called the stable base locus. And in fact, it does not have, it has some properties which are not so intuitive, or at least they did surprise us. So let us start with the definition of the base locus for a vector E. This is the set of points in X where the evaluation on global sections, so the map from H0, XE to the fiber EX, is not surjective. Not a surjection. So this is a subset in X, and this has a natural subscheme structure, which is given by the fact that it does correspond to a linear series inside the line bundle. So this is, if we look at the map, if R is the rank of the vector bundle E, we can construct the linear map from the exterior product R times of the vector, many dimension vector space of global sections of it to the global sections of the determinant of the vector bundle. So it has as a map a subspace of global sections of the determinant. And therefore, the base locus of this linear series is exactly the place where these do not generate the determinant, and therefore where this map is not surjective. Okay, now for line bundles, the stable base locus is the intersection of all the base loci of all the higher power of the line bundle. Then we can do the same thing for a vector bundle, but considering symmetric power. Why this? Because we remark that in this projectivization of vector bundle construction, when we look at the direct images of the twisted of O1, so O1 twisted with O1 m times, then this is isomorphic to the symmetric product of it. And then this implies that when we look at the global sections over PE of OM, or PEM, then this is isomorphic to the global sections over X of the M symmetric power of E. Also, we remark that if we consider the symmetric power M times of this vector space, then this has a natural map to the space of global section of the symmetric product of it. So this map in general is neither injective nor surjective, and some authors relate normal generation of the vector bundle E exactly with surjectivity of this map, as in the line bundle case. Okay, and then we can define, according to this construction, the stable base locus as the intersection of base loci of all these vector bundles. So we define stable base locus for vector bundle E as VE being the intersection for all positive M of the base locus, all the base loci of sim M of E. Then this is a closed subset of X, and of course, for example, it is vanishing if and only if a given symmetric, well, by neutrality, let's say this would be equal to some finite intersection, as it is a chain of closed subsets. And then this is going to be empty if and only if some symmetric power of E is globally generated. Using this kind of construction, we defined also the augmented base locus and the restricted base locus of E, using, let's say, the base loci, instead of considering the symmetric product of E, we twist them times an ample line bundle plus or minus some power, positive or negative, of a given ample line bundle. This is and in fact we did prove that these loci here are related to some of the positivity properties. For example, such as thickness, ampleness, netness, and so on. Today I want to restrict my attention to the stable base locus of And so therefore, I don't want to give the definition of this one. But the first behavior of the stable-based locus that did surprise us is the following. The peculiarity is the following. While for so the augmented and restricted base loci, they live inside here, and also the stable base locus. Then we have the corresponding loci for O1, OP1 inside here. Augmented and restricted, they behave well according to the projection type. In particular, we have when we look at the image of the augmented or restricted base locus of O1, the line bundle of PE, then this is exactly the augmented and restricted base locus of E. Therefore, there is I mean, this could even be taken as a definition. What happens is that if we look at O1, also for the base locus of O1, the same thing happens. The image of the base locus of OPE1 is the same as the base locus of E. A surprising fact is that the same does not apply for the stable base locus. So in general, we have that the image of the stable base locus of O1 is just included in the base locus of E. But it can be different. And I want to give an example of this first fact. This first fact did surprise us, and us were me and Ordinati, because, for example, what does it mean that this locus is empty? This locus is empty, it means that some symmetric product of E is generated by its global section. So it's globally generated. What does it mean that this locus is empty? It means that same thing, but for O1. So in particular, O1 is semiample if some higher power is globally generated. And in the literature, in some places, we found a different definition considered as equivalent. So we say that E is semiample either if this O1 is globally generated, or if some power of this O1 is globally generated, or if some symmetric power of E is globally generated. And therefore, this means semiample either if this is empty or if this other one here is empty. However, we did find out with a simple example that this is not always, they are not always agreeing, and therefore it can happen that this locus here is empty while this is. I want to give a very simple example of this fact. And if I have time, I would like to give later on a much more geometrical example of the same thing. So an example of some vector bundle whose symmetric power are never globally generated, but such that the symmetric powers or the potential powers of O1 are globally generated, and this with a symmetrical meaning. First, I would like to give an easier example that will show us why we have to take care of the definitions when we want to talk about semiample vector. So let us start to provide this example with a smooth projective curve of genus greater than 1, greater or equal than 1. Then we can fix a line bundle L, which is a two-torsion non-trivial line bundle over X. So L is non-trivial, but L squared is trivial. Okay, it is immediate to check that any symmetric power of the vector bundle E, which is OX plus L, will not be globally generated. And this simply because the symmetric power of E, in this case, are all of the form OX, direct sum L, direct sum L squared, which is trivial, direct sum, and so on, until L to the power M. Therefore, there is always a copy of L inside all symmetric powers, and therefore this has no global section because it's a non-trivial torsion line bundle, and therefore the global section of this are zero. Therefore, global section of this can never generate the whole vector bundle. However, simply because L is a two-torsion line bundle on X, we can consider a 2-to-1 cover where L does trivialize. So there exists a 2-to-1 map from another curve X tilde of G greater than 1. Think about, for example, an elliptic curve and two torsion line bundle and a 2-to-1 isotropic. Therefore, there exists X tilde with a 2-to-1 cover such that F star L is trivial on X tilde. And therefore, this means that F star E is trivial again, because it will be OX plus X star of L. Therefore, it is OX. In particular, F star of E here, this is trivial, but in particular, it has the O1, which is a semiample line bundle over the E. So we consider the projectification of this one, projectification of this one. Here we have the O1, and then one can check, the construction of projectivization is a universal construction. And therefore, one can check that the O1 goes back to the O1 for this one. So F star of O1 is the same as O B F star E 1. This is the thing. And then under a surjective map, something is semi-ample here, if and only if it's full, but it's semi-ample in here. And therefore, we can say all this tells us that O E 1 is semi-ample. And in fact, one can even check that in this case here, O PE 2 is the base point. So concerning base loci, we can say that in this example here, since this on the global section of this are always lacking a component, then the stable base locus of it is always the whole manifold X, because there are no points of X where the global sections surject of over the final on no points. So all X is all points of X are base points. However, base locus of the E2 and therefore the stable base locus is X. Then this brings us to make to consider two different definitions of semiamples. So we should consider a definition of semiampleness where we suppose the symmetric power of E to be globally generated, and then a definition where we suppose the symmetric power of O1 to be globally generated. And we will call them respectively weak semiampleness or strong semiampleness. We will use these as definitions. We will say that E is strongly semiample if the symmetric power of E is generated by global section, so globally generated for some positive n. And we will say that E is weakly semiample if OPEM is generated by global section. So it's base point free for some positive n. And remark just that the global sections of this one and the global section of this one are isomorphic. Just that we're picking different evaluations. And then we just showed that we can have weak semiampleness without having strong semiampleness. The convex is always, I mean, the other implication is always working out, because if we consider strong semiampleness implies weak. In fact, if we have strong semiampleness, it's globally generated. This means that on X, there is a surjective map from a vector space V times tensor OX to sim M of E. Okay, now when we look at phi star E, these are vector bundles over X. When we look at pi star E, we know there is a surjection to OPE1. And therefore, when we look at symmetric product of that, we have the symmetric product and times of pi star E, which is the same as pi star of symmetric product of E, surjects to OPEM. And therefore, now over PE, since there is a vector bundle generating this, we pull back this surjective map and we have the V times OPE surjects here, and therefore it surjects even here. And so this is a globally generated line bundle over P. So the comment does always hold. Okay. The fact that I was saying these definitions are similar, they concern the same vector spaces, but just different evaluation maps, led us to consider explicitly what are these different evaluation maps. And here we come to Iitaka fibrations. And so let us see what these are. So we want to, yes?
So one example, your vector bundle has a component sample picking, which is a line bundle.
Yes.
Can you formulate these conditions to line some?
If R, so you mean, suppose that every line bundle is, suppose that every line subbundle of E is semiample. What happens in that case? Let's see. Well, I mean, it cannot be stated in this way, okay? Because of course there will always be some I mean, yes, she means sub-bundle. I don't know. I mean, might be because eventually, I mean, what does this mean when this? It's always. I mean, there are always some. I mean, not that intuitive. What does it mean that this is not surjective? It means that this map here maps to a hyperplane inside here. But this doesn't imply that is exactly the point why the two things are not equivalent. This does not imply that it is contained in something that comes from a sub-object of B. Okay, so I mean, you have to look directly at symmetric MOV. So, I mean, that characterization, I think it wouldn't be that easy. Okay, so we were talking about evaluation maps. And therefore, second part, Iitaka fibration. So, the main idea of Iitaka fibrations for line bundles is that we have to look at the Kodaira maps, which are exactly the evaluation maps considered in family. Kodaira maps to the projective space, and then we consider higher power of the line bundle, and we want these maps to stabilize to some given map, and eventually show it is effective. Okay. So let us try to do the same thing here. We can define a Kodaira map. Which are the following. Consider E a vector bundle. The base locus of E is the locus where E is not globally generated. Out of the base locus of E, we can consider the evaluation maps. So to a point X, we can associate the evaluation map on X. And this is a quotient of the sections of E to some vector space, which is exactly E. So to each point of X, we associate a quotient, and such a quotient is a point of a Grassmannian. So we have a map from X minus the base locus of E to the Grassmannian of quotients of this space of dimension R. So maps from H0 X E to quotient spaces of dimension R. And this is what we call the Kodaira map. Now, this, of course, it is a rational map in general, and the locus where it is defined is exactly X minus the base locus. So now, suppose that the stable base locus of it is not the whole variety X. So suppose we can consider two different settings. The first one is the strongest one. So let us suppose that the stable base locus of it is M. This means that at some point there is some symmetric product of it which is globally generated. And then we can fix an integer M in the set of all integers where the symmetric product is globally generated. So all integers M such that Sym of E is globally generated. Consider this set. And for each M in here, we can define a Kodaira map that is a regular map, because now we don't have base loci, right? It will be a regular map from X to some Grassmannian. Now the dimension of this Grassmannian, they grow, because this will be the Grassmannian of a global section of Sym E, but the quotients have a growing rank. The growing rank will be let's say, the rank sigma mr, where sigma mr is the rank of the symmetric product of an r-dimensional vector space. Therefore, sigma mr is m plus r minus 1 over r over m. And anyhow, the rank of the symmetric product of E. So the question is, how do these maps behave asymptotically? Do they stabilize? And if yes, where? Then we can consider a slightly more general case, which is what if this law, this this one. So we can consider a slightly more general case. So what if the stable base locus of E is not the whole variety X? What does this mean? That some symmetric power of E is not globally generated, but there is an open subset of X where the global sections over X of the symmetric power of E, they generate the symmetric only over a smaller, an open subset. So the second question would be, if the stable base law of E is not the whole variety X, then we have this phi m, which are just rational maps toward some Grassmannian, the same Grassmannian. Okay, and then we can have 10 questions. So, how do these maps behave asymptotically, growing, letting m grow? And then finally, we could prove with Stefan Ordinati a theorem that tells us that essentially the same behavior of codiagram maps for line bundle hold for vector bundles with some So, as in the case of line bundle, there is a difference between the semiample case and the general case. Here, let us place ourselves first in the semiample case. So suppose that E is strongly semiample. This means that the stable base law of E is empty. Then there exists a normal variety that I will call YG. And there exists a regular map from X to YG that I will call phi G, which will be such that for all m in this set of integers where the symmetric product is globally generated, the codiagram map phi m, which is a map to some well, we could consider either just its image inside a Grassmannian or the normalization of its image. In any case, this map factors through a finite map. So there exists a given regular map such that for all codiagram maps, these codiagram maps, they factor through this regular map and a finite map. And this is the first part of the construction of the Iitaka fibration. Okay? So phi m, so for all m, phi m as nu m after phi g with nu m. Okay. The second thing we could prove is that this map here is not really far from the codiagram, the Iitaka fibration map of the determinant of the action. This means that it is not the same, but there is another finite map through which the map phi g factors. So part B the theorem. We can remark that as my hypothesis E is strongly semiample, this means that the symmetric product of E is globally generated, but therefore also the determinant of E is also some power of the determinant is globally generated. So E strongly semiample implies that the determinant of E is a semiample line bundle. Okay, and therefore, as a semiample line bundle, there exists an Iitaka construction for the determinant of E. And this Iitaka construction, I will call it phi infinite, from X to Y infinite. This is the Iitaka fibration. For the line bundle determinant of E on X, which is a line bundle of X on X. And then what I say is that this map, the map phi g factors through a finite map from the Iitaka fibration of the determinant of E. Okay, but this means that the asymptotic of the Kodaira maps for a vector bundle are not really different in this case from the asymptotic of the Kodaira map in just looking at the line bundle, which is the determinant of it. And the reason for this is that this is the asymptotic, but you can think about this as some phi n. Therefore, the image is contained inside the Grassmannian. If we look at the Brucker embedding of the Grassmannian into some objective space, then the natural O1 of the projective space pulls back to the determinant of the line through all these maps. Okay, so this is the reason. However, this is a finite in general. This is a finite map, but it's not an isomorphism. Therefore, this means that this asymptotic is slightly this asymptotic here is slightly different than this one. But it also means since this is a finite map, while this is a fibration, this is not a finite map. And even we could consider the sign factorization of this map, and it could be exact this one. So this said, this construction doesn't tell us much more than the Iitaka construction, but it's random. And the last part, as in the case of Iitaka, we can consider this also in a binational. So when the Kodaira mass sets rational maximum, this happens. The table-based knowledge of it is not necessarily empty, but it is smaller than the whole variety. So this means we call this asymptotically, generically generated. This means that there exists some high enough M where the global sections of the symmetric product generate X only. Okay, well, in this case, these constructions hold, let's say, birational. So there exists a commutative diagram in the following. I mean, it's really it's really the generalization of the Iitaka one. So we have there exists a birational map, a regular and birational map with some normal variety xg, and there exists a regular surjective map xg to some yg, such that this asymptotically is the Kodaira maps. So this means that for each m, where the base locus is not x, and for k big enough, we consider the Kodaira maps by kn. They have some in y km, so these are just rational maps, but these are birational to this. Therefore, there exists, this is given, and for each k and n, there exists this Kodaira map and a birational morphism with yg in such a way that this diagram. So here is regular and birational. Here is regular, and here is birational. For each m and for k big enough, we can construct asymptotically we had one realization, birational realization of asymptotic big enough. Yes. YKM for a given m and for k big enough, this is birational. This is just a rational map. So you can imagine what happens in the line bundle case. So the Kodaira maps are always rational. In general, they're rational. They're not well defined because the line bundle is not say by n. And however, for big enough, now there is this slight. This has been improved somehow. We could just say for n big enough, we could have this. Okay, but I wanted to be more consistent with what I want to describe. Okay, so these are the two. These are the constructions that we made, the Iitaka constructions, and I want to sketch just an idea of the proof, which is a big diagram. Because in this diagram, one can see exactly the only difference with the line bundle case. And the diagram is somehow related to Veronese embeddings, which is what happens for line bundles if you consider higher power of the line bundle and its global sections and the evaluation. So let me try to construct this diagram. First, I will and explain what are all the maps of the ring. So basically, we have a given map phi m, and then we want to consider the higher power multiplied by k. So we fix, let's say, m in ME, and then we consider all positive k, and then consider k bigger than 0, and the Veronese maps. I call Veronese maps. Not used to write. By this, I mean the following: if we have evaluation on global sections of S and E, so it's this map here. Okay, this is a map of vector spaces. It is a surjective map. When I consider the symmetric products, I still have a surjective map. And therefore, starting from this, I obtain a map from Sk of H0 Sme to Sk of Sm of E. The problem is what Camilla called Platism. The problem is that Sk Sm of E in general is surjects, but it's not the same as Skm of E. Or, I mean, here we have an X, the fibers over an X, since this is the evaluation on X. This is not the same as Skm of Ex. It is the same if E has rank 1, because all these are rank 1, one-dimensional spaces. And therefore, one has to take in account this kind of construction. But what about the evaluation maps for this here? Well, the evaluation map for this, I mean, given fixing a point X, we have various evaluation maps. We have this one, we have the evaluation maps in here, but we also have the evaluation map in there. And if we know that the evaluation map is surjecting here from global sections, then also in here, I mean, from this one to this one, it will be surjected. And therefore, what we have is that we have for an evaluation map X, we have the following: Sk of H0 of Sm of E. This map here, one can show that it surjects to Sk of Sm of Ex. Yes. And then we have another surjection to Skm of Ex. Okay. And then one has to consider also another map, which is the following. When we look at the the symmetric product of global section of SME, so this space here, then this has an image which is inside the global sections of the evaluation, this one and of this one, or the global section of that one and of that. So, in particular, it has an image W inside H0 of Skm of E. Okay. So these are symmetric powers of global sections. These are global sections. This is symmetric power of global sections, and these are fibers of some vector space. And with these ingredients, we can construct a big diagram. Which is the following. Put together all of these evaluation maps and then see whether we can factor out some finite maps. Now the diagram goes as follows. Start from X. We suppose M is an integer such that Sm of E is globally generated. And therefore, we have a map to some space Ym, which is inside a Grassmannian of H0 Sme, quotients of this one with rank sigma n of R. Okay, now we can consider a kind of Veronese embedding of this one inside a Grassmannian of Sk of H0 of X of Sn of E. Simply take the symmetric product of the maps, of the quotient. So with S sigma K of sigma M of R. And one can see that this Ym, since it's the inclusion, it will be isomorphic to some Y1 inside here. Okay, now I have to consider also the map. So this is the map phi m. Now I have to consider the map phi km. Some y km, which is inside the Grassmannian of H0 S km sigma km of R. And now, looking at this subspace W, since we have W inside here, when we look at the quotient of this one with the given rank, we have a projection to the quotient of W. So we have a projection here to the Grassmannian quotients of W, which is this W over there, of the same rank, sigma Km R. And now one can show that actually this map here, this is an affine map, and this map here, when we look at the quotient, gives us an isomorphism of this with some manifold I call Y2 twiddle. Some variety over there. And now, how do we relate this map here with something which lies inside the Grassmannian of Sk of H0 and ME, which corresponds to this quotient here. So Sk of H0 SME sigma Km R. Well, simply we do have a surjective map here to W, and therefore we have an inclusion of this one inside here. Okay, and therefore we have a Y2. It lies inside here. This inclusion. These sorry. Here are not isomorphic. This is the finite map. This is a finite map because it is affine and it is well defined everywhere. So it is affine and it is a projective map. Okay, so now I have these two maps here. This is a map to this Y2, which is phi Km and after a finite map. And this is phi m. So now I have to consider another manifold, F, which is the flag manifold corresponding to this sequence here. So here we have, and I don't want to get into the details, but we do have a flag manifold with two maps here, phi 1 and phi 2. And when we look at the image of X inside this flag manifold, it means to each point X, we associate this sequence of maps of vector spaces. We don't have an image that I did call Y hat KM here. And now we can show that this is an isomorphism and that this, the white one, is a finite map. Or necklace. So we have nu1 and nu2. Therefore, looking at all these compositions, we have a map, then composition with finite maps, and then Ym. So this is the basic idea of the proof of the fact that when we look at each phi m here, it factors through a given map. Why is this? Because for each pi m, this taking all the km is factored through finite maps. So there cannot be an infinite chain of finite maps, and therefore it must stabilize to something. And then for k big enough, it is a given statement. Okay, so this is the idea of the construction. Now I have